Let's get right into it. If you're studying for your clinical exercise physiology exams or you're an exercise science student, you've definitely stared down what looks like, well, a terrifying wall of metabolic math. But today in this explainer, we're going to completely demystify ACSM metabolic calculations. We're transforming what feels like an overwhelming memorization nightmare into a highly intuitive, repeatable skill. So let's dive in and conquer this math once and for all. Now, I want to start by asking the million-dollar question that plagues almost every candidate sitting down for these exams. Why do most people fail the ASMM metabolic equations? You might think it's because the algebra is just too complex or that memorizing the equations themselves is impossible. But honestly, that's a massive misconception. The real culprit? Unit errors. Seriously, unit errors cause the vast majority of wrong answers here. The math itself, it's just basic addition and multiplication. But look, if you plug miles per hour into an equation that secretly demands meters per minute, your entire calculation collapses. It's like putting diesel in a gas car. So the absolutely crucial takeaway today is that mastering these equations isn't really about the math at all. It's about locking down your units before you ever touch that calculator. Here's our mental roadmap for today's explainer. We're going to cover 1. The universal building blocks. 2. Essential units and conversions. 3. Walking, running, and stepping. 4. Leg and arm cycling. And finally, 5. The 4-step problem-solving method. Starting with Section 1, the universal building blocks. I want you to think of every single formula as a simple 3-part construction project. You have a resting component, a horizontal component, and a vertical or resistance component. When you stack those 3 blocks together, the sum always equals your gross VO2, which is expressed in milliliters of oxygen per kilogram of body weight per minute. If you can just keep these 3 distinct buckets in your head, you can construct literally any equation on the fly. And the absolute magic number here, it's 3.5. 3.5 milliliters per kilogram per minute equals exactly 1 MET, or metabolic equivalent. This number is your rock. It acts as the constant, unchanging resting component in every single equation we're going to look at today. No matter what crazy exercise your client is doing, they are always burning 3.5 just to stay alive. It's the base of our entire blueprint. Now, here's a quick trap to avoid. When you add up the blueprint, the equations give you gross VO2. That's the total oxygen cost, which includes that resting 3.5 we just talked about. But if an exam question asks you for the net VO2 or asks you to calculate caloric expenditure for the exercise alone, you've got to strip away that resting 3.5. Net is just the activity's cost above rest. So simply put, gross minus 3.5 equals net. Keep that in your back pocket. All right, moving on to Section 2, essential units and conversions. Drill this first constant into your memory right now. 26.8. If an exam gives you treadmill speed in miles per hour, do not use it. You must convert speed into meters per minute by multiplying your miles per hour by 26.8. For example, 3.5 miles per hour multiplied by 26.8 gives you 93.8 meters per minute. That is the number you actually plug into your blueprint. Okay, here's your next essential tool, 6.12. When you get a question about a stationary bike, the work rate is usually given in watts. But guess what? The ACSM equations strictly require work rate to be in kilogram meters per minute. To bridge that gap, you always multiply the watts by 6.12. So 150 watts times 6.12 equals 918 kilogram meters per minute. See? Easy. Let's rapidly lock down the rest of these crucial conversions. First up, always convert a treadmill grade percentage to a decimal. So a 10% incline, that becomes 0.10. Next, to convert your final VO2 into METs, you just divide by 3.5. If you need absolute VO2 in liters per minute, multiply by the person's body mass in kilograms, then divide by 1,000. And lastly, for caloric burn, remember that 1 liter of consumed oxygen is approximately equal to 5 kilocalories. If you lock these down, those tricky unit traps just vanish. Section 3, walking, running, and stepping. Notice the beautiful symmetry here. For both walking and running, the resting component is our constant, 3.5. For walking, the horizontal cost is 0.1 times speed, and the vertical cost is 1.8 times speed times grade. Now for running, because of those bounding mechanics, the horizontal cost actually doubles to 0.2 times speed, while the vertical cost drops to 0.9 times speed times grade. Oh, and here's a vital tip. If your client is walking or running on a flat 0% grade, that 0 completely cancels out the entire vertical component. It just wipes it out. Now, stepping is a bit of a different beast.
So let's deliberately slow down to unpack it. It still follows the same blueprint. Resting is 3.5. The horizontal component is 0.2 multiplied by your stepping cadence, so the steps per minute. But the vertical component introduces a totally unique mechanic because stepping involves both stepping up and stepping down. So it's calculated as 1.33 times 1.8 times the step height times the steps per minute. And hey, a massive warning right here. Your step height strictly must be in meters, not inches, not centimeters, meters. Don't let them trick you.
Let's roll into Section 4, leg and arm cycling. As we shift over to machine-based modes, we really need to contrast the mechanical factors of the bikes themselves. These are absolutely critical for calculating your initial work rate if it isn't just handed to you in watts. Remember that work rate equals resistance in kilograms times the flywheel distance times the pedaling cadence. For a standard Monarch leg ergometer, the flywheel travels exactly 6 meters per revolution. But an arm ergometer flywheel is smaller. It only travels 2.4 meters per revolution. You really have to know which machine you're calculating for before you start doing the math. Okay, here is arguably the biggest quirk in the entire ACSM lineup. When we look at leg cycling, there's an oxygen cost just to move those heavy pedals with your legs even if there is zero resistance on the flywheel. This is called unloaded leg cycling, and it gives us a horizontal component value of 3.5. So your leg cycling equation actually begins with 3.5 for resting, plus another 3.5 just for unloaded pedaling. Arm cycling, on the other hand, is much lighter and has absolutely zero horizontal component. Finally, let's look at the third block for cycling, the resistance component. For leg cycling, it's 1.8 times your work rate, divided by body mass in kilograms. For arm cycling, because the upper body is just mechanically less efficient, that multiplier jumps to 3.0 times the work rate, again divided by body mass. Notice here that unlike the upright modes of walking and running, the resistance components for cycling strictly must be divided by the subject's body mass to get that relative VO2. Section 5, the 4-step problem-solving method. All right, let's bring it all together. Here is your foolproof 4-step method. Step 1, read the prompt and instantly identify the mode. Are they walking, stepping, or arm cycling? This dictates your entire blueprint. Step 2, and I'm leaning in heavily here because this is literally where exams are won or lost. Convert all units first. Change MPH to meters per minute with 26.8. Change your percent to a decimal. Change watts to kilogram meters per minute with 6.12. Step 3, only after your units are clean, plug them into your resting plus horizontal plus vertical equation. And step 4, check what the question actually wants. Your formula just gave you gross VO2. Do they want METs? Divide by 3.5. Do they want net? Subtract 3.5. Do they want calories? Find the liters of oxygen and multiply by 5. And that brings us to our final thought for today. The ACSM source material clearly warns that these equations are a skill. They are not just a set of facts you can skim over once. So ask yourself, are your steps automatic yet? Take the blueprint from this explainer and immediately practice the mixed problems. Force yourself to convert those units first, plug them into the 3-part block second, and adjust the final output third. Practice this until it's second nature, and I promise you will never fear a metabolic calculation again. Keep learning, keep focusing, and I'll catch you in the next explainer.